Okay, so good evening all. This is NOC 26 W86 NPTEL tutorial session on semiconductor devices for next gen field effect transistors, more than mood, a physics perspective. Okay, so the course instructor is Professor Sudeb Dasgupta from IIT Roorkee. He is a well-renowned professor in India and abroad as well. He primarily works in associated with okay. Anyone else going to join? Okay, sidebar. Right. So I see one person joining. Ananta. Can you unmute and introduce yourself?
Yeah, I'm from NIT Calicut. I'm in my final year, so I decided to take this course because I'm interested in it.
Okay, so you are in NIT Calicut.
Yes, sir.
So your department is ECE, I presume.
Yes. Mm-hmm. Yes, sir.
So you are interested in higher studies?
Yes.
Okay, fine. So shall we start or should we wait for some time?
I think we can wait for some 5 minutes or so, sir.
Okay, fine. So you are aware, right? This session generally happens at Saturday 3 to 5. So
Yes,
last
sir.
week I was traveling, so I had to reschedule it.
Uh, that
So tomorrow
explains.
there is another session, right?
Yes, sir.
Okay. So you had your placement session over?
I'm actually not sitting for placements because I plan to go for higher studies.
Okay, in India or abroad? What is your plan?
Sir. Yes, sir.
Okay, fine. That's good to know. You are interested in VLSI, right?
Mm. Yes, sir.
Okay. So I think we can start. Basically, people can join and they
Yes, sir.
need to catch up. No need to
Mm.
wait, right? Okay,
Yes, sir.
so as I was introducing the course, this is NOC 26W86 NPTEL tutorial session on semiconductor devices for next gen FETs, more than more, a physics perspective. So the course is taken by Professor Sudeb Dasgupta. He is from IIT Roorkee. He is a senior professor and well renowned in India and abroad. I am Debashish Nandi from IIT Kanpur. I am a final year PhD student. So I did my bachelor's in from NIT Durgapur back in 2017. Then I was in industry, telecom R&D. Then I switched back to I applied for direct PhD and now I'm in IIT Kanpur. So anyway, let's start. So it is a 12 weeks course and we go live every week from 3 to 5, right? So I hope that you are you have enrolled for the course and also doing the assignments,
Yes,
right?
sir. Yes, sir.
So the primary focus of this session would be to I will tell you some kind of problem solving, but will give you some hidden concepts, right? I felt that in my bachelor's also there are some gaps between the concepts and what actually there is, what we are taught and what there is. So I'll try to patch that up. And also, if you have any questions during the session and regarding the lectures, you're free to ask. So first thing is that what do you understand about this thing? I am sure that you are familiar with field effect transistors. So just take to, by the way, I want to make this session interactive. No, just treat me as your peer, your fellow student. Okay. So we can have a chat and discussion. So that is the better way to, uh, how should I put it? Break the ice and get the concepts more clear. Okay. Is that okay with you, Anand?
Okay, sir.
Yeah. So, what is field effect transistors? Any idea?
Yes, sir. Basically, a transistor is a device which can switch on and off when you apply a particular type of voltage.
So that can happen in BJTs also, right? That we call bipolar junction transistors. So how do we differentiate between field effect and this?
Well, in field effect transistors, it should, we say the transistor is on when the voltage you applied one of its terminals is greater than a particular threshold value.
No, no, that is fine. So, see, whenever we ask, for example, we introduce some, we join some nouns and create and some abbreviation, right? It has some more fundamental meaning to it.
Okay. Yes,
So,
sir.
you have any idea where electric field can be sustained? Any kind of device you are familiar with? Where electric fields can be sustained. See, I'll go from very basics, okay? So any kind of device you know that you have breadboarded in your UG course as well, I am pretty sure. Any kind of device that comes to your mind where you draw the electric field lines. So what are the basic passive devices you are aware of?
Passive device includes substances as resistors.
Right, resistors. Then
Then let's see. Uh,
passive means no power is getting generated, right? If I plot my IV characteristics,
Capacitors.
if I plot my IV characteristics in this fashion, so it should lie, if I follow passive sign convention, it should lie in third and this quadrant, right?
Yes, sir.
Or any input and output relation for that matter. So, any idea other devices? You know about this, right? Capacitance and
Yes, sir.
inductors. These all are
Yes,
passives, right?
yes, sir.
So, among these three, there are, I can give you other examples. For example, diode is also a passive device, right?
Yes, sir.
Not your solar diode, because if you see your solar diode characteristics, it this quadrant it comes to your fourth quadrant, and there are actually what that power generation is happening in the solar cells. Okay, so not
Yes, sir.
that one. So any among these devices, in which one you have in your 11th, 12th, in which one you have drawn electric field lines? In one case, let's say forget about resistance, right?
Yes,
That
sir.
is a simple device, very simple device. It is not so simple if we come to if we make it with semiconductors, but let's say we have made it with the insulators, and now among capacitor and this inductor, so you have drawn magnetic flux lines through inductors, right? You remember wrapping up a wire around the pencil solenoid and all, and you draw the
Yes.
magnetic flux lines, right? That is on magnetic field basically. So how about capacitance? So capacitor, generally if we talk about parallel plate capacitor, so you have something like this, right? This is if you apply some voltage. So let's say the plates are of metal, so positive charges accumulate at this one, negative charges accumulate at this plate, and then you say that your electric field lines are like this. This is your electric field. I hope you have seen this.
Yes, sir.
So this basically is your field effect, okay? So in MOSFET, what is happening? When you apply, let's say this is your MOSFET structure. So do you see a capacitor here? This is your source, this is your drain, this is your body, and this is your gate. So do you see any capacitance here or capacitor for that matter?
The oxide layer.
Exactly. So this across this, you will have that. Basically, we know, right? By applying a voltage at gate, I can turn on and off the transistor and control the flow between the source and drain for, let's say, source and drain. So what is happening? So you are controlling charge at the plate of the capacitor, right? By some electric field which is sustained across an insulator. Is that clear? So
Yes, sir.
that is why it is called field effect. Okay, that is why it is field effect transistor. And in BJTs, it is primarily governed by your p-n junction theory. So that is why historical for historical reasons it is called junction transistors, and bipolar because two types of carrier drift diffusion, and you know about that, right?
Yes,
So
sir.
another thing, do you see any p-n junctions here? Let's say this is
Yes, sir.
NMOS.
Source and drain.
You have p-n junctions, right?
Yes, sir.
But that is not controlling your transistor action. That is controlling the leakages and all that we will discuss later, right?
Okay.
So the primary action is what? Transistor is like a switch. I turn on or off some, I give potential to some node, and between some other two nodes, current will flow. And that current flow, how much current will flow, I am controlling via the voltage at a third terminal. That is a transistor action, transfer of resistance. That will come to later. Okay, why it is called transistor and all. But be sure that this is why it is called field effect transistors. Okay. So then what about more than Moore? What is this? Have you heard of anything?
Yes, sir. It
So
states
is
that
this
the law which states that the number of devices will double every 2 years or so.
right? But what is Moore?
More was a scientist than man who generated Gordon Moore.
Uh, okay, yeah. So you know about Intel, right? So he is
Yes,
one
sir.
of the founder of the Intel, company, Gordon Moore. So what he did, he was asked in 1965 to write an invited paper in one of the premier conferences in our field. Okay. So what he observed that if we plot, he had only 5 data points. Okay. So he plotted and he had seen that in a given area, number of transistors are doubling almost every 18 months, right? So that is why it is called Moore's law. It is widely known as Moore's law. So how did we achieve that?
By shrinking transistor size.
In what dimension? Transistor is a 3D material, right?
In
So
length,
if
sir.
length,
Channel
right?
length.
Why length?
Because the width is too small, I suppose.
Sorry?
Because the width is almost too small. So we only have like 2 dimensions in the
See,
transistor device.
this is the
Yeah.
dimension where your transistor action is taking place. This is another dimension and this is another dimension. This is width direction, this is
Hmm.
length, and this is your thickness. Okay. So why in length direction? Do you remember the how do I put it, the current equation, MOSFET IV equation?
Yes, sir.
What is it?
Half mu n C ox W by L VGS minus VD square for saturation.
That is in saturation, right? Half mu n Cox dash W by L VGS minus VTH whole square, right? And if you have CLM, then you have this lambda VDS.
Yes, sir.
Fine. So where does this L come from?
L comes from the channel length.
This is the channel length, right?
Yes, sir.
So what I wanted, what they wanted to reduce the power consumption as well, right? So how do you reduce the power consumption? Your power is basically nothing but VDD times ID, right?
Yes, sir.
You will get to know that this guy VGS
Hmm.
is getting lowered, but you need
Hmm.
to somehow keep your ID higher to get a feel around about the same kind of same kind of power level that you are handling. So
Okay.
one way is to increase your W, another way is to decrease your L. There are other ways. We are just talking about 2 degrees of freedom. So what will happen if I increase my W and keeping my length fixed? My transistor size will increase, right?
Yes, sir.
That means what? To perform one single operation, I need a larger area. That is not what we desire, right?
Yes.
So another way is that I am shrinking my length or lowering my length. And lowering length helped in achieving two things: higher density of transistors on a chip or IC, and what is the other thing that we are getting achieved by lowering that length?
Reduce power.
Any okay, less power, let's say less power. And what is the other thing? So you see that this is N plus, right? And when current will flow, there will be a channel between these two. It's like a pipe between the two layers or two tanks. What
Yes,
is
sir.
happening if I reduce, this is my length? What will happen if I reduce my length? So this is, let's say this is your source and this is your drain, right? So electrons are traveling from this to this.
Hmm. Shorter time, so it will take a shorter time to
That
be drawn.
means
Better switching action.
speed is increasing, right?
Yes, sir.
So what is the simplest way to understand this? Your I is Q by tau. If let's say for the time being, let's assume that it is linear, right? Otherwise it is dq by dt. For the time being, let's assume that it is q by tau, and tau is that time what the one electron takes in average to travel from source to drain. So if I can reduce that tau by reducing L, you understand, right? Assuming that your drift velocity is constant,
Yes.
right? Velocity is length by tau. So if my
Hmm.
length is reducing and this Vd is constant, that means what? Tau is also reducing. That means my
Yes, sir.
speed is improving, right? This is a simple way you can explain, let's say in
Yes.
future, wherever you have your interviews and all and whatnot, right?
Yes.
So that is what Moore predicted. That is how the transistors, a more number of transistors were we were able to get as an
Hmm.
semiconductor industry during that time. We just shrink the length and then whatnot, right? But what will happen, as I have told you, that these are two physical, let's say these are PN junctions, right? So of course there will be some depletion region, correct?
Yes, sir. There will be some
So
depletion region.
now if I reduce my length, what will happen? Let's say I am keeping making this shorter, shorter and shorter, and
Then the
let's say
depletion.
this kind of thing is getting created.
Yes, sir. So it will
That
be
it
uh,
will
so
be
it will be more
it will be
increased.
what will be increased?
The depletion regions would.
Depletion region, let's say bias and all, everything is constant, doping is constant. Your depletion region width is what? Something Q times Na, then your 2 times epsilon silicon times some potential, right?
Yes, sir.
So let's say this is constant, this is constant, depletion width is constant, but I'm reducing length. Basically, I'm keeping putting my source and drain closer and closer. So what will happen? What did I want at the first place? I wanted a third terminal to control the current flow between first and second,
Hmm.
right? So this is basically your gate, this is drain, this is source, this is what is your transistor action. But that will happen only when I can control this region by this guy.
Yes, sir.
Now let's say you are putting your source and drain so close that any potential you apply, right? This is drain and source. This field, electric fields from this is reaching altogether to your source. So what will happen? Your VDS. So what did I want? I wanted that VGS, or let's say for the time being, let's say VG, voltage applied at gate terminal, to control IDS, right? This is what I wanted. But as you keep your as you kept your decreasing your length, so your VDS will start to dictate the current flow, or IDS. So basically what it is becoming, if I give you a device where the current flow is being controlled by the potential applied across it, what is that device?
Now just now is just a basic resistor.
That is a resistor, right? Exactly. So it is losing your, that is becoming a resistor. So it is losing your transistor action and becoming a resistor as I keep lowering my length. You have read about channel length modulation and all, right?
Yes, sir.
So what is happening in channel length modulation? If you draw your ID VD for a long channel device, you have read that this is what your device looks like.
Hmm.
So this is your IDVG, IDVD characteristics looks like for a particular VG, let's say VG1. Why I am keeping this? VG1. And now let's say in short channel devices, it is becoming like this. That much you are aware of, right? This is channel length modulation at the same VG, but here this is for L2, this is for L1, and L1 is much greater than L2. This you are aware of?
Yes. Yes, sir.
So Let's say I take this region. So in the blue curve, what we are seeing in the blue curve, if I take any 2 point in that yellow region, so is my current changing with VDS? Is my current changing with VDS?
Yes, sir. For the closed, so yes, sir. When we have that shorter lengths, it will change. Yes, current will
For the
change.
shorter lane, it will change, right?
Yes, sir.
So that means you see this action is basically you are leaving your transistor action towards some resistive action, right? So that
Yes,
is
sir.
why if you draw the small signal model, you would have seen that there comes a small resistance RDS, right? This is your GM VGS, that is the
Hmm.
controlled current source,
Hmm.
and this is the additional resistance. So you are
Yes.
losing your transistor action. That is the main thing I wanted to highlight if you keep lowering your length. So that
Okay.
means what? I am losing the fundamental effect that Gordon Moore had predicted, that I will not be able to get a denser chip with more transistors, right? So what is the solution? I need to find out some other way, right? To keep lowering my length as well as improve my transistor action so that it does not become a resistor. Is that
Hmm.
okay?
Yes, sir.
That is what this course is all about. Okay. So
Yes, sir.
this is what we call that more than Moore. So this is the professor Dasgupta has designed this course in a way that he starts with very basics and keep on increasing. The learning curve will be exponential. Okay. So make sure that you try to get grasp as much as possible. This is primarily a PG course, but a good thing to know before you go into research. Okay. And we'll mostly talk about your basic semiconductor physics, which you already know. There will be nothing extraordinary that you don't know. And that is why it is physical, will give you the physics perspective. Okay. So shall we begin?
Yes, sir.
Okay, fine. So once this title is cleared, and so next gen, by the way, next generation means you're already in research, already in research, but it is yet to be translated into production, right? There is a time between research and getting the product at hand. Anyway, so let's begin. So, okay, I have one blank page. So just get it here. Okay. So yeah, so these are customary that links and all will be provided to you by the team. So yeah, so I think this will be some MCQs, some warm-up questions. So which of the following is true for unipolar devices? Any guesses? I think
Sir,
this
I would say the
is
first option is correct.
so.
Current flow
What is unipolar? What do you mean by unipolar?
will flow only in one direction. Current flows only in one direction.
No, that is not fundamentally true. What is a dipole?
So there will be two charges, right, sir? One will be positive, other will be negative.
Dipole is there will be two charges separated by some distance, right? And there will be some
Yes,
sustained electric field. For example, in your ferroelectric materials, right?
yes, sir.
These are dipoles. So what is a pole? basically? Pole is basically polarity of charge.
Yes, sir.
That means either it is positive or negative, right? What you have told is correct, but that is the consequence of what unipolar device means, right? That is not the definition. That is
Hmm.
the consequence. So unipolar device means a device where the current flow is controlled by one type of carriers. Okay, either holes or electrons. So you understand, right? In semiconductors we have both type.
Yes, sir.
Why do we have so, if I may ask?
Well, in semiconductors, there's only one type of mobile charge carrier, that will be electrons. The other one is source, which is created as a result of this movement of electrons.
uh the second part I could not catch.
The holes, okay, holes are just created when an electron just leaves its, when an electron just leaves its particular orbit or something.
Right, but how does then hole takes part into conduction?
It will be due to the, okay, sir.
So electrons are free, right? It will get some energy, it will go to conduction band, it will have too many empty spaces or empty states, energy states, it will move around. But what
Yes,
about
sir.
holes?
Holes will be generated because the electrons are leaving a particular position.
Right? Electrons are leaving, right? There is a
Yes,
vacancy that you are telling it is a hole.
yes,
But
sir.
hole, to carry current, hole needs to move around in the semiconductor.
Yes, sir.
So how will it move around? First thing, tell me, does it move around?
Yes, sir, it will move.
Of course it will move. If it is carrying current, it has to move, right? Next
Yes.
question would be why it is moving. Basically, hole is what? Let's say you have too many
Positive.
silicon bonds, right?
Yes, sir.
So you have silicon bonds. Let's say it gets sufficient thermal energy so that one electron leaves. It will leaves means it will be in the crystal. But what does a free electron mean? Free electron means it is in the crystal or the semiconductor, but it is not bound to some particular atom. Okay,
Yes, sir.
that is a free electron. So what about a hole? So it will create a hole, a vacancy.
Yes.
So now how will this hole move around? So basically, if this is a vacancy, that means there is a positive charge. So the electron from this place can go to this place,
Yes, sir.
and that will result to a creation of hole here. So this is effectively that hole is moving in this direction.
Yes.
So imagine a situation where you have a tube filled with water, a glass tube filled with water, or even you can consider a bottle, right? A bottle, and there is a bubble. So if you just turn the bottle upside down, the bubble travels to the other part. This is the same thing how the holes are moving in the crystal. Okay. So holes are also taking part into conduction.
Yes, sir.
So semiconductor by default is a bipolar material. Means either bipolar means there will be carriers of both type, right? So if there are carriers of both type, but in some cases, if one type of carrier is more than the other, then we call it the amount, the majority part of the carrier. Suppose in semiconductor I have 10 to the power 15 this electrons. Somehow, let's say by doping, I have 10 to the power 16 electrons. and I will have 10 to the power 15 electrons, then I will have, of course, by law of mass action, you know, that at equilibrium I will have 10 to the power 5 holes, right? So if I have
Yes,
10
sir.
to the power 5 holes and 10 to the power 15 electrons, so I can easily neglect the amount of current that the holes will carry. It will be very minuscule. Primarily, it will be governed by electrons. So then that transport, we call it as a unipolar transport, or that those devices where one type of carrier dominates, that is unipolar transport, right?
Yes.
So current flows due to one type of charge carriers, either majority or minority. So it is true. Then current flows due to both majority and minority carriers. It is not true. Otherwise, we would call it bipolar. BJTs are called unipolar devices. By definition, BJT is bipolar devices because they have two PN junctions back to back, right? So electrons and holes both are traveling from one side to another, right? If you see the current density plot across any PN junction, you will see that the total current is sum of Jn and Jp, right? If you are not familiar, just have a quick revision. So this is also not true. Current does not flow in this kind of devices. So if we have charged carriers, if we apply potential, if we give the material carriers room to move around, or you can control their directional flow, then I can have current. So there is no point to not have current. So the first option will be right. Okay. So what about the second question? When silicon is doped with dash and dash, a p-type or n-type semiconductor is formed. So what is the fundamental thing that we need to know here?
Sir, we need to know which are donors and which are acceptors.
Uh,
Total.
in another way, that first thing we need to know, silicon is a group 4 element in periodic table.
Yes, sir.
So that means it will have 4
Yes, sir.
electrons at the outer shell, right?
Yes, sir.
And silicon, it will be like there will be another silicon, there will be another silicon, right? So, and these are the covalent bonds, right? It needs to fill up and make it with 8 electrons, right? That is the condition where it will be stable.
Yes, sir.
So, what happens if we dope it with some group 3 element? And what
Sir,
do I mean by doping it with group 3 element?
that means only three electrons will take part in bond formation.
So, you mean to say, let's say I am doping it with group 3. Tell me any group 3 element.
Boron.
Okay. So, let's say boron. So, let's say boron is here. This is boron, let's say. So, boron will have 1, 2, 3. So, 3 bonds, 3 covalent bonds are there, right? So,
Hmm.
what about the other bond?
That will not be filled. That will lead to a hole.
It is not like that. That will be filled. That, let's say, that will be filled with some electron, but then my boron is negatively charged ion, and this electron will come with another hole. Okay.
Yes, sir.
So if it is empty, understand this very carefully. If it is empty, then my system is not stable. It has to have 8 electrons, right?
Yes, sir.
Across the bonds, across one boron atom, it has to have 8 electrons. So you cannot say this is empty. So that electron and hole pair, that electron and hole pair will come from some other place. We are not concerned about that. So that will take, this electron will come and take this place. However, and this hole will be very nearby to that atom. Why it will be nearby to that? Because now my boron is negatively charged, right? So boron is one negative charge and I have a hole vacancy. Do you understand?
Yes, sir.
Now if I need to have these holes free, I need to increase the temperature of the device. Okay. So this is what is happening with group 3 element. As you have said, boron is one example. And what about this group 5 element?
So when a group 5 element forms a bond with the silicon, then one of the electrons will be
Example.
okay. That will be like phosphorus, sir. Any group 5 element like phosphorus.
Okay. So let's say phosphorus will have 5 electrons, right?
Yes, sir.
So 4 will take part in bonding and 1 electron will be additional.
Yes, sir.
And what about the phosphorus atoms polarity?
Be negatively charged.
It will be positive, right? It is having additional electron.
Okay.
Phosphorus ion is positive. You see, boron ion is negative. So what is happening? There is a boron ion and then there is a hole. So there is one attraction force. Similarly, if you have a phosphorus, you will have an electron, right?
Yes, sir.
So generally people, students do this mistake or commit this mistake. So that is why I am explaining this thing in detail. Okay.
Yes, sir.
So that is one thing. So how come it will become P type or N type? That is your group 3, that is your group 5 case. So how will it become P type or N type? What does that mean, P type and N
Because
type?
P type because its hole and holes are considered to be positive. N type because electrons are negative.
So can you tell me one thing that how many atoms are there in silicon per centimeter cube? What is the atomic density?
Where 1.5 into 10 power 10, that will be the
No,
intrinsic
no,
concentration.
no. That is intrinsic carrier concentration at room
Hmm.
temperature. I
Okay.
am asking how many silicon atoms are there in 1 centimeter cube volume of is any silicon block, let's say, silicon crystal. I am asking about silicon atoms, not carriers. How many silicon atoms per centimeter cube? You know about Avogadro's number, right? 6.023 into 10 raised to 23
Yes, sir.
elements per mole, right? One mole has that many number of uh, particles, let's say. So I am asking in that range. So what is the silicon's case? Silicon is 5 into 10 raised to 22. Okay, this is atomic density.
Yes, sir.
So what kind of doping you are aware of,
P type and N type doping.
right? But what is the value? Give me some value. What you have seen, numerical value. What kind of
Uh,
doping you have seen? Let's say
10
this will
power,
be acceptor, this will be donor. So what is the this Na and Nd value typical range?
10 power 15.
Let's say 10 power 15 per centimeter cube. That means how many, let's say, let's talk about P type, okay? Let's say how many boron atoms per centimeter cube in this doping? It will be 10 to the power 15, right?
Yes, sir.
Per centimeter cube. Fine. But what about the silicon? How many silicon we had?
10 power 22 initially.
10 raised to
5.
22. It will remain 10 raised to 22. There is nothing initially, okay? It will remain 10 raised to 22. So now, can you appreciate this fact that you have this kind of silicon bonds? So this is just pictorial representation, okay? So actual bond looks like something we call a diamond lattice. You remember, right? CH3 methane, 109.4 degree tetrahedral
Yes, sir.
shape, right? It is something like that, but it is a 2D projection, top view. So let's say if you have this silicon like this, so how many boron atoms in how many silicon atoms? 10 to the power 7 silicon atoms will have one boron atom. Do you get that?
Yes, sir.
That means what? In a sea of silicon atoms, you will have, let's say, one boron atom. And if you are, assume that you are standing in that boron atom's place. So if you look around, you will not see another boron atom until
Hmm.
unless you cross 10 to the power 7 bonds. That is 10 to the power 7 per centimeter cube. But if I boil it down to, that is 3D, right? In one direction it will be that by 3, that means 7 by 3. That will be around your 10 after, let's say, 1000 silicon atoms. If you start walking in this direction, after 1000 silicon bonds, you will see one this another boron atom, right?
Yes, sir.
So this will come into our discussion of mobility. Somebody wants to join. This will come into our discussion in mobility. So this is kind of an precursor. So how do you think this doping happens? Basically, you have one pristine intrinsic kind of silicon, right? Silicon crystal. You apply some kind of ion implantation or diffusion or some gas, high energy gas of boron you are pouring on top of that, and those borons are going in and making it p-type material. Okay.
Yes, sir.
Now understand one thing: which boron atoms will be there, means which boron atoms will be important for that p-type semiconductor. Those, only those who are coming and knocking out the silicon atom, right, from the bond and substituting that silicon atom with a boron atom. There will be plenty of vacant spaces. If you see the silicon bond structure, it is something like this in 3D. So these spaces are free. These spaces are free. There is nothing inside. Only the boron atom that knocks one of the silicon atoms that are sitting at the bonding position will actually be important to us. What about the other boron atoms which are not knocking this? By the way, these boron atoms are called substitutional. Okay, and the other boron atoms will be somewhere here in the vacant spaces. They will be just like sitting idly, not creating any bond, not taking into any chemical, not taking part into any chemical reaction. Okay, these are called interstitial. We will come to this why it is important. Okay, so understand that many of the boron atom will not knock the silicon atom. Only those who will knock the silicon atoms out of the bond and occupy that place will take part into creating that p-type or n-type semiconductors. Is that clear? And though that boron atoms, the concentration of those substitutional boron atoms is this value, not the total boron present in that semiconductor bar. Is that okay?
Yes, sir. Sir, I just want to ask one question, sir.
Yeah,
Is there a particular criterion for a particular boron atom to actually, to actually be a substitution?
there are criterias. Of course, there are criterias. But see, you are not hitting it with one particular boron atom, right? You are hitting with an avalanche of boron atoms. Throw everything, let somebody get into the position of that silicon atom and knock that out. And that silicon atom will also be in that substitute in that interstitial void. Okay, it has to have that energy, it has to have that directionality. You, how do I put it? This is not the course to discuss those things. You have heard about this packing densities, Miller indices, and all crystallography you have done.
Yes, sir.
So in those crystallography, you know about these planes, right? Where you can chop off the material.
Yes.
So if something is coming perpendicular to that, then that impact will be different. And if some boron atom is coming, it is a gas. Understand that this is a gas. It is a Maxwell-Boltzmann gas that you are putting into the throwing it towards the silicon, right? Depending upon what you cannot exactly calculate, but you can have a fair idea that how much energy of that electron gun or that boron gun you require to knock out those silicon atoms. Okay, so the key takeaway from this is the more the doping, also more the interstitial this atoms. Okay, so this is what we mean by p-type or n-type doping. Okay,
Yes, sir.
so as you have rightly said, a p-type, because silicon is group 4, a p-type will have a group 3 and n-type will have a group 5 element. So this one is 3 and 5. This is the correct one. Aluminium and boron. Aluminium is also type 3. It's joining this late. So aluminium is also type 3. These are both are type 3. Both type 3. This is metal, and I'm not sure about its position in the periodic table at this moment. This is type 5, group 5. So I should write group 5. This is just the opposite. So this is not true, this is not true, this is not true. Only this option is correct. Okay. So moving to the next question. So the threshold voltage of an N-channel enhancement mode MOSFET is 0.6 volt. When the device is biased at gate voltage 3.3 volt, pinch off would occur at drain voltage of, so any
2.0.
idea? Why do you
Yes,
say
sir.
so?
So pinch off will occur when when the voltage drains VDS equal to VGS minus VT, sir.
And why is that? There is a fundamental assumption behind that. Can you tell me that is what that is? So we are talking about something like this situation. This is your, let's say, this is an exaggerated diagram. Your inversion charge is almost like a sheet, thin sheet. So it is, don't take that it is physical dimension of the charge, okay? This is just a blown up image. So what is this negative signs? What is this negative sign inside a circle?
That means electrons.
No, these are
Fixed
called
charges.
acceptor ions, right? This is the same thing as this guy. That is why I was showing you this boron at this place will have a minus sign. It is an ion. That group 3 element will be an ion, right? So be
Yes,
very
sir.
clear about that. That ion is not moving around. Why it is not moving around? Because it is having 8 electrons at the outer shell. Shared 8 electrons. It is stable. It is not moving around. To get that to move around, we need very high energy, right? Before that, lot of things will happen. So these negatives encircled signs are dopant ions. We call it dopant ions. For acceptor, it will be negative. For donors like phosphorus, it will be positive. Fine.
Yes, sir.
Now, what is threshold voltage? Threshold voltage means that voltage where
Precipitation.
electrons start to appear, or the type of the substrate will start to invert at the interface. This is the interface. Most important part in our discussion. Why it is interface? This is SiO2 and silicon interface. Okay, fine.
Yes, sir.
So now this is, let's say, Vg. This is, let's say, Vd. So you have told that when your VGD is equal to VTH, then will pinch off happen, right?
Yes, sir.
So that will give you your VD to be VG minus VTH is equal to 2.7 volt. Is that okay? That is what you have said, right?
Yes, sir.
But what is the key to this point is that this region, if I zoom, this is N plus, and you have, this is, let's say, your inversion charge, and here you will have your oxide, and let's say here you will have your gate. So this is your VG at this point, and at this point you have VD. So this is VD. So what are the things you are assuming? You are assuming that this potential is directly appearing at this node, right?
Yes, sir.
And how can you make that approximation? You can make that approximation because you have electrons or kind of n-type material throughout this region. If I take a cut section at this location, so what will I see? And if I draw that doping profile, I will see throughout this is n, and this is also, let's say, n plus, it will be slight bump. This is also n plus. That means what? I can assume this n and n plus as a too many electrons. N plus means too many carriers, right? Towards your metallic kind of region. So that means what? Whatever potential I apply at this will appear at this location. Then I consider my MOSCAP, MOS capacitor, threshold voltage condition or definition, and apply it here. We will discuss this in detail. As these are warm-up question, I just wanted to check that how much in how much depth you know the subject. I'll explain accordingly. Okay. So you understand, right? What is the conditions we have? We need to have, so this is the line across which, let's say A bar, across which I am plotting doping concentration, and this is this direction X. Okay. If it is P type, then I would have something like this. Then whatever potential I'll apply, it will not reach at this position because this is my P type. So then there is no question, or you cannot use this formula then. Okay, we'll discuss this thing with detailed band diagrams and all. Okay. So 2.7 is the right answer, provided that there is no voltage drop in your drain. That means in this region there is no voltage drop. This is 0, and in this region the surface has already inverted, or the p-type substrate had become n-type. Is that okay?
Yes, sir.
Fine. So then next question: threshold voltage of a p-type MOS capacitor is dash if the doping concentration of the substrate increases. So p-type MOS capacitor is a two terminal device. So this is GMOS MOS capacitor. So what is the, this is, let's say, silicon. So what is the type of the silicon in case of a p-type MOS capacitor?
So it will have a p-type substrate.
No. What is this? This is PMOS or NMOS? This is NMOS, right? Or N-channel MOSFET. This can have two meaning. Okay, in that sense you are talking about. Okay, that is also fine. So if you say so, okay. Anyway, so if you can consider this as P type MOS capacitor. Hmm, Adding this for the first time. Anyway, P-type, if we are considering, let's assume body is P-type. Okay. So what is the threshold voltage? I just want to check whether you have studied or not. What is the threshold voltage formula?
Sir, 5, okay, 5 flat blunt.
Wait a second. What is threshold voltage? What voltage is a threshold voltage?
So for N type, it was
No,
amount of
no,
voltage at,
not anything. Voltage means what? I am applying either at this terminal or at this terminal. I have only two terminals, right?
yes, sir.
So what is VTH? Which terminal voltage is VTH?
So gate terminal.
It is some VGB, provided this is the reference potential. You can say that it is the gate terminal voltage. Is that clear?
Yes, sir.
So it is some VGB. Okay, let's start with that. It is some VGB. So if I have some VGB, where will my potential can drop?
It drop to the bulk.
One drop will be across the oxide layer,
Yes.
and another drop will be, if it is P type, so I will have acceptor ions, right? So another type will drop across the acceptor ions. This psi ox is oxide potential. Psi S we call it surface potential. Okay,
Yes.
we'll discuss all this. So why it is so? Because let's say I apply a some positive voltage. So what will happen? Metal will have these charges, positive charges, right?
Yes, sir.
And I will have some sort of negative charges here as well. Let's say electrons also started to appear.
Mm.
How will my field lines look like? Electric field lines, how will it look like?
From the positive to the negative.
From the positive to the negative, right? So
Yes, sir.
how will from positive to negative it will be? This
It
can
will be
have
passing
one,
through the plus
this can
side.
have one, this can have
Mm.
one, this can have one. So it will be
Mm.
spreaded all through, right?
Yes, sir.
If electric field, so what is the relation between field and this? Let's say psi is your potential, some potential. If E is some electric field, and let's say this is the direction X. Okay. So how will my electric field at any position relate to potential? Electric field
That
at any
depends
X
on
will be,
ratio of voltage difference to that of position. dV by dx.
is that okay?
Yes, sir.
So you understand that throughout this location, throughout this location, electric field is not zero.
Yes, sir. The electric field won't be zero.
There are electric field lines, right? So that means this is not equal to zero. What does that mean? I have psi. Can I write psi not equal to zero?
Yes.
Not in all case. There will be some exception, but in general sense, I can write that generally psi is not zero. right? That means potential is not zero.
Yes, sir.
That means when you started answering the question, you told me that it will be in the bulk, right? But now you are seeing that electric field lines always has to pass this oxide layer. That means some potential has always to be dropped across the oxide. Is that clear?
Yes, sir.
So the total potential I'll have this, this one and this one. Okay.
Yes.
Now there is something called contact potential. Generates when generates, let's say, at heterojunctions. What is heterojunction? Two different type of material I am joining. So this becomes a heterojunction. Okay. So because their work function and Fermi levels are different, when you make a complete system and keep it in equilibrium, so their overall Fermi level has to be constant at a single Fermi level. That creates this potential and your bands will align. Okay, we'll discuss all this. So that is one work function. I am assuming there is no charge in the oxide for now. Fine. So this will have how many component? This contact potential, then oxide potential or
And surface
potential
potential.
drop across oxide, and your surface potential, right?
Yes, sir.
This guy is called VFB, phi ms component of VFB. This oxide potential is psi ox. This surface potential is psi s. Fine. Now,
Yes, sir.
when threshold voltage in threshold voltage condition, so this VTH you write it as VFB plus psi s at threshold plus psi ox at threshold. So we'll show this later that this can be written as this psi s becomes 2 phi f or let's say phi b, and this psi ox is nothing but gamma square root of 2 phi b. Your phi b is nothing but thermal voltage times natural log of doping with respect to intrinsic carrier concentration of the silicon at that temperature. Okay. So this is called flat band voltage. And where is this voltage coming from? This is the drop across the contacts, right? Heterojunction. That is where I was trying to bring this concept to. 2 phi b is what? This is the surface potential or this drop. And this is your, what do we call it? Oxide drop. Is that clear?
Yes, sir.
Now the question is, so okay, I have not introduced gamma, right? So gamma is a constant that is square root 2 epsilon silicon q doping divided by Cox dash. So dash I will write when it is normalized to area. This is epsilon oxide divided by
Right.
Tox. Okay. Generally capacitance is epsilon A by D. I am writing only epsilon by D. That means I am writing capacitance by area, per unit area, right?
Yes.
Okay. So in VTH, if I write VTH as a function of Na, okay, just let me change the color so that it is not confusing. If I am writing VTH as a function of Na, so I have VFB plus I'll have, let's say, 2 phi B, which is also a function of Na. Then I'll have gamma, which is also a function of Na, times square root of 2 phi B, which again is a function of Na. So which one do you think dominates?
So the left term. No, the rightmost term. Gamma Na times root 2 phi BNA. That oxide drop term.
This is one term, this is another term. Why do you say so? What is the
Because
dependency of phi B with respect to Na? What is
phi
the
B
function?
just down Na, sir.
That is logarithmic,
Just
right?
logarithmic, yes.
And what is the dependency of gamma with respect to Na?
Square root of logarithm.
Why square root of logarithm? It is only square root, right?
Just for that gamma. The gamma is just square root of Na.
Square root.
Hmm.
Which one is a strong function? Which one is stronger? Logarithmic or square root?
So logarithmic.
How does your, let's say, f of Na, g of Na? This is Na. So how does square root look like? Right? Parabola,
Yes.
right? Is it clear? Y equal
Yes.
to square root x. That means x square equal to y.
Hmm.
Just it will not have the second half, right?
So how is it x square equal to y? Shouldn't it be the other way around, x equal to y square then?
Oh, yeah, sorry. So y equal to square root x. So x equal to y square. Yeah, correctly pointed out. X equal to y square, right? That otherwise it will be like this. Is it okay?
Yes, sir.
What about logarithmic?
That will be y equal to e power x.
That will be y equal to,
Ln x, which means x equal to e power y.
that means x equal to
E power
e
y.
power y, right?
Yes, sir.
And how do you plot that?
That will be an exponential increase.
That means it will be something like this,
Yes, sir.
and this increase, as it is exponential, it will be very sharp. This is one, right? Is that okay?
Yes, sir.
Clear, right?
Yes.
So which one is stronger function?
Square root.
This one is stronger, right? So that means when I am talking about this VTH NA dependency, which one should I focus? I should focus this one. Okay. This I am telling upfront because this will be required later in the course. Okay. That how to deal with, there will be so many dependencies, interlinked dependencies. You need to understand which one to consider when and make appropriate approximations. Okay. For that, I am telling you like this is the way to think about it. Always to better to check with some kind of plotting tools like your Desmos, MATLAB, Mathematica, whatnot. Fine.
Yes, sir.
So if n increases, gamma increases, gamma square root of 2 phi f increases. That means psi ox increases. That means VTH increases. So threshold voltage increases, right? Right?
Yes, sir.
The physical way to think about this is suppose you have a 10 to the power 15 doped p type silicon and in another case 10 to the power 17 doped, right? So when you will have these positive charges, you are applying positive voltage at the gate, right? In which case you need more positive charges to cater for this depletion. Forget about the electrons, forget about these guys. This will come later. After the depletion is saturated, then it will come. We'll learn about that. What is surface potential, pinning, why it gets saturated, and all, right? But whenever you are applying positive voltage at the metal of the MOSCAP, you are having positive charges at that capacitance plate. So two and electric field lines is getting generated, right? That electric field lines to cater for that, it needs to get terminated somewhere. An electric field line will terminate at the negative charge. And where will you get that negative charge from? That you have two options, either B minus ions or your acceptor ions or your Na is the doping, or let's say this is only boron doped. So either that negative charge will be supplied by this B minus ions or electrons, right? But understand it is a p type semiconductor, so obviously your electrons are very less. So what is the easiest way or the least energy path for that electric field lines to get terminated in a negative charge is your B minus ions or acceptor ions, right? Now if you have more
Yes.
number of acceptor ions, then to nullify that negative charge you need more number of positive charges or more voltage at the top gate. That means your threshold voltage is increasing.
Yes, sir.
Okay, that is the physical interpretation. So the transconductance of an n-type MOSFET in linear region is, what is the equation IDLIN? What is the IDLIN equation?
For the linear region, it was mu and C ox W by L
Hmm.
into VGS plus VT
VGS minus VT
in
ti-
plus
times VDS
minus
minus VDS
VDS
square
minus.
by 2. Is it not?
Yes, sir.
So what is GM transconductance?
Will be the ratio of output current to that of input voltage.
So output is my drain, right?
Yes, sir.
With
Drain
respect
current.
to my input voltage,
VGS minus VT or just VGS.
that is VGS. So this gives me mu n
Mu and
C ox W by
into
L VDS,
VDS. Option 3.
right? So you have studied two port networks, right?
Yes, sir.
So what is this corresponding to? Which parameter? Quickly tell me.
So it will be corresponding to that y parameters.
Right? Y parameter. Which Y parameter? Let's say output port is 2 and input port is 1. What parameter will it be?
So
Let's
that
say
will
you are
be
at that frequency where
y2.
capacitance are all open. So it is purely your admittance is purely
Output current to the input voltage. No,
right.
that will be
So
y2
what
not
is the real part of admittance?
real part of
So let's say Z is impedance, right? How do you write it?
R
R
plus jxl.
plus Jx. What
Yes,
is
sir.
R?
That will be the resistive part.
What is X?
Can be either inductive or capacitive, reactive.
General term I am asking. It is very important to understand the terms. This is what?
Impedance.
What is this?
Propagation constant.
No. Y is admittance.
Okay. Sorry, that I thought was just gamma, sir.
G is
That will be transconductance.
that is
Conductance.
conductance. Why transconductance? So if you understand the nomenclature, no, 80% of the doubt is gone. What is this? B. Susceptance. It is called susceptance, right?
Yes, sir.
So I am asking you that GM is relates to what? GM is a conductance, right? First thing it is a conductance. Second thing it is a transfer conductance or transconductance. If this is your Y parameters, if this is your port 2 and this is your port 1, so GM will be nothing but Y21 or real part of Y21. Is that clear?
Yes, sir.
Right? In other sense, when can I ignore this? When can I ignore B? At low frequencies. Assuming no inductor is present at low frequencies, my capacitors are open, right?
Yes, sir.
That will leave me X equal to,
So that will be zero by itself. 1 by j omega c.
so your B will be 0. So that is at low frequency, real of Y21 will become Y21. That is how you measure your high frequency parameters in case of MOSFETs as well, okay? So understand whenever you are studying no transconductance, always related to your Y21 two port parameters. Fine?
Yes, sir.
Okay. So okay, then the MOS capacitor reaches a threshold voltage when,
So this is the onset of inversion.
and how do you know it is onset of inversion?
So
Have
we
you
can tell
drawn
it is
have you
it will be an
drawn band diagrams of
having
MOSCAP?
yes, sir.
So what is the first criteria to draw a band diagram?
We'll be having three regions: metal, oxygen, oxide, and the semiconductor.
Okay, so let's say you have metal, you have oxide, you have semiconductor. So metal oxide, let's say semiconductor P type. Fine. What is the first line we draw? Let's say these are three separate systems. Okay. System 1, system 2, system 3. They are separately, individually at equilibrium. Fine.
Yes, sir.
What is the first line we draw in case of a band diagram?
Fermi level.
No.
Okay, that will be the vacuum level then.
Exactly. First line we draw are vacuum level, because vacuum level is same for all of these. Vacuum level has nothing to do with the materials, right? By definition, it is in vacuum. So next, what you draw? Let's say for system 1, as it is in equilibrium, you draw the Fermi levels, right?
Yes, sir.
So let's say this is your EF, this is your EF. For insulator, there is no concept of Fermi level. We'll come to that, right?
Yes,
Let's
sir.
first start with okay. Just assume that this EF metal and EF semiconductor are at the same level. What is this distance called?
So metal work function, sir. Work function of metal 5M.
No, this is Q phi m. Phi m is the unit is volt. This is
Okay.
energy what we are drawing, right?
Electron volt then.
Yes. Q takes care of the electron part. Fine. So what about this? This is semiconductor work function. Okay, we'll come to that later. Now, what is the next line you will draw? Where will the EC lie for metal?
So it won't have easier. So it will be lying with the vacuum level itself, right, sir?
No. So that is why I was drawing this, right? If you have, let's say you have three types of materials, right? Metal, insulator, and semiconductor. So this is the conduction band. For insulator, let's say this is also the conduction band. This is also the conduction band. For semiconductor, this is your valence band. For insulator, this will be your valence band. What about metals?
It will be So there will be kind of intermixed with one another, right, sir? Conduction band and valence band.
There can be one
And
case where there can be an overlap. Another case can be conduction band, very narrow separation of valence band. Now, what is this range? This is at the thermal level, right? KT. KT means what? Room temperature, you have that particle has that energy KT in 1 degree of freedom. In 3 degree of freedom, it is 3 by 2 KT, right? In 1 degree
yes,
of
sir.
freedom, it is around half KT, right? If it is gaseous,
Yes,
for example. So we'll just remove the half and for discussion's sake, we'll consider KT. So if it is in the KT region, KT gap, so at any T, that particle will have sufficient energy to move between conduction band and valence band. Is that clear?
yes, sir.
So that is how metal is looking like. So what we are concerned with, we are concerned with these levels. So these are the band edges, right? EC and EV. So why we are concerned with minima of conduction band and maxima of valence band? Can you tell? why we are bothered with minimum of conduction band? Why not the maximum of conduction band?
Maximum conduction band extends to infinity.
Sorry?
Maximum conduction band extends to infinity.
No, it does not extend to infinity. That is what you assume for calculation of the solving that integration, right? It does not at all go to infinity. Maximum band of conduction band. It is a band. Understand? It is a band, right? It has certain minima and maxima. It never goes to infinity physically. So, what is the fundamental law of physics? Every particle likes to take the minimum energy, right? Likes to
Yes,
stay at
sir.
the minimum energy. So, what is the minimum energy in the conduction band? Where the free electrons will move around is EC, right? Is it clear?
Yes, sir.
This is the minimum energy of free electrons. And why we are bothered with conduct valence band maxima? Because valence band is that band of electrons of which will take part into the chemical reactions. That is the definition of valence band, right? Or valence electrons. We have studied in our chemistry 9, 10th and 11th, 12th courses, right? That valence electron are the most interesting one because they take part in chemical reactions.
Yes, sir.
So beyond this, everything is stable. You will have orbits and whatnot. So the outermost part of that orbit, electrons of that orbit, will take part into chemical reaction. That is being represented with your valence band and EV. That is why we are considerate about this EV, valence band maxima. Fine. Now tell me where will the conduction band of the metal lie in the right hand side image? Any idea?
So will it lie on the surface of the metal itself?
No, no, there is nothing. We are talking about surface of the metal. It is
And it
throughout
will
the metal.
coincide with the Fermi level.
Exactly correct. What about valence band?
Valence band will somewhat be close to it or could overlap with it.
That means I can safely assume EC, EV all will be at the Fermi level, right? For metal.
Yes, sir.
For this, I will have something like this: EC, EV, high band gap, right? And for
Yes, sir.
semiconductor, I will have something like this. As it is p type, so my Fermi level will of course be closer to the valence band.
Yes, sir.
Is that okay?
Yes.
Nice. So fine. So some other dimensions. What is this?
Electron affinity Q chi bar.
Q chi, right?
Yes, sir.
What is this?
5 FP.
EG, right?
No, no, EC minus EV. That is band gap. Band gap.
That is band gap. Fine.
Yes, sir.
So if I tell you that Q chi and EG, these are called material properties, okay? That means as long as we are inside the material or one material is concerned, this will not change inside that material. Is it clear?
Yes,
Irrespective of what you dope it with, what you give your this, whatever you give your bias, ultimately it is silicon. Ultimately it is metal. Ultimately it is SiO2, right? So what are not changing? These
Uranium.
guys and this are not changing. Fine. Now what about this?
Fires is not exactly a material property because it will depend on concentration, right, sir?
Concentration, bias and whatnot, right?
Yes, sir.
This is called induced property. Okay. Phi m fairly remains constant because it is again the only property that the metal has, right?
Yes, sir.
Fine. So if you understand this much, now tell me what will happen if I join all these three?
So it will lead to a sharp edge for that oxide part, and there will
Wait
be
a
band
second.
bend.
No, there is no band bending. Why there will be band bending?
So there won't be any band bending because in this case, all the Fermi levels are perfectly aligned.
Right. So let's say what I want to do. Okay, just let me remove all this. So now I want to join system 1 and system 3 and make it one system. This concept is very important of the system, okay? This is important in case of your understanding the equilibrium. So first, and if that is the case, what is the first line we draw when we have a heterojunction? This is heterojunction, right?
Yes, sir.
So what is the first line we draw?
Fermi level.
Right. By the way, what is thermal equilibrium?
No current flows through.
No, no. Fundamentally, what is thermal equilibrium? I'll give you some very interesting things, but hold on for that. Thermal equilibrium means no source of energy except constant temperature. Fine?
Yes, sir.
No net motion of carriers across any interface. Net any. No net flow of energy across any interface. And this two gives the final condition, principle of detailed balance. What is that? Have you heard of that?
No, sir. I've not heard about it.
Principle of detailed balance means suppose you have one phenomena across a cut section, right? You are telling me that okay, the cut section is vast 1 centimeter square. That is why I am not having no net motion of carriers or energy. What about I shrink it down? Will it still hold? As that area of that cross section you can take at any place, any size, these two will still hold. Okay, this is called principle of detailed balance. Fine. These are the four conditions of your thermal equilibrium. So now tell me, if you can see a semiconductor bar, will that be in equilibrium at constant room temperature?
Yes, sir. It will be in equilibrium
No, the answer is not. How can you see a semiconductor bar? What is the fundamental thing that needs to be allowed if you want to see a semiconductor bar?
it shouldn't allow any flow of current
No, no, no. If you can see. How do you see things?
with our eyes
How do you see things with your eyes?
because of reflection of light, sir.
Right. So light has to be present.
Yes.
So if you can see a semiconductor bar, that means some light is reflecting on the semiconductor and getting into your eyes.
Yes, sir.
So that means my first condition is being violated, right?
Yes.
What is my first condition? No other source of energy except constant temperature. So if you can see one semiconductor, that means what? There is presence of light, another form of energy.
Yes.
That means it is not in equilibrium.
Okay.
You understand, right?
Yes.
So understand what equilibrium means, fine? And in another term, Fermi level slope is zero. That means Fermi level is constant. Fine.
Yes.
Fermi level represents the average energy of the electrons in a system or fermions in a system. Fine.
Mm.
So in a system, so it is very important to understand what your system is. So now I'll have this. This is my Fermi level. Fine. So I'll just draw my this, and I had this, this, fine, and let's say this was my E0. Now this is my EC, this is EC, this is EV, this is EC, this is EV. So if I ask you, see, I know that you know these kind of things, but let's say before today's discussion, if I would have asked you that what is the EC track, I would have asked that trace EC or conduction band edge from metal to semiconductor. Just draw that line. Most of you would not be able to draw that line. What is that line? Where will it start? Tracing EC and EV across MOS capacitor. So EC will start at here. There is a jump. So this is how your EC looks like. Fine.
Yes, sir.
And how about your EV?
There will be jump downwards, then those jump upwards.
Right? So when we will discuss later gate tunneling, or tunneling through any potential barrier. So you see potential barrier, right? Electrons at this cannot cross to this because there is a potential barrier, right?
Yes, sir.
So whenever we will discuss about gate tunneling for thin oxide devices, then my barriers will be EC will be something like this, because this is my TOX, right?
Yes, sir.
If TOX is lesser, then quantum mechanical tunneling can happen, and that leads to flow of current.
Yes, sir.
Okay, so it is very important for you to understand how EC and EV looks like even in flat band condition. Fine. Tomorrow I will discuss about accumulation, depletion, and others, and also solve uh, questions related to MOS capacitors. Okay. Meanwhile, I will stop today, and this is also called. Okay, I'll introduce flat band tomorrow because there are some other catches in that. Okay. So I hope you found it useful. If you have any
Yes, sir.
question, we have 10 minutes still.
No, sir. I understand now.
Okay, so if you have any question, right? So, okay, just let me do one more thing. So this is my email ID. So if you have any question, you can send me an email if you need clarification regarding this subject, or if you need assistance in studying other subjects. So I can patch you up with some good resources. Okay, and feel free to ask questions. Okay,
Sir,
I
where
also,
was the mail
yeah,
ID that you shared? Sir, where was the mail ID you shared?
there,
Oh,
can you not able to see?
okay. Okay. Just thought I was in some chat or something.
Ah, okay. No, no, it is on the screen. Because I'm
Okay.
recording this so that the other students may also be will be able to see that.
Hmm.
Okay, so do well, study well, and let me know if you find any difficulty in understanding the concepts. Fine.
Yes, sir.
Yeah, more advanced stuffs will follow. Yeah. Okay. Thank you for joining, and hope you had
Thank
a
you.
good time.